Okay, so our next stop is space. What edge computing can learn from the moon landing? 2019 marked the 50th anniversary of the first moon landing. Decades later, the Apollo program still stands as one of the community's most impressive technical achievements. Space travel is one of the earliest examples we have of connected devices and distributed computing, a real precursor to IoT and Edge. Many of the lessons learned during the Apollo program are still relevant today. So this is the theme that our next speaker, Frederic, would explore. So Frederic, welcome.
Thank you, Philip. Really appreciate the opportunity and hello, everyone. So my name is Frederic Desbiens, or Fred. I'm program manager for IoT and Edge computing at the Eclipse Foundation. And the whole point of this presentation is really to explore what happened during the Apollo missions and see the lessons we can learn today in terms of edge computing. So let's get started right away. If you're not a big space buff, let's start by explaining a few things about the vocabulary I will use during this presentation. So essentially, if you read a bit about the moon missions, there are obviously several pieces of hardware involved, but the main ones are the ones you see on the slide. So on one side, you've got the common module and the service module together. So the common module is the little capsule, right, where the astronauts were spending their time, and the service module is the reminder of what you see. And essentially, it contained equipment, fuel tanks, oxygen tanks, that kind of stuff, and lots of obviously scientific equipment that was used throughout the mission. And together, they were certainly the part of the spacecraft. Well, only the common module came back to Earth. The capsule was the only part of the spacecraft that was designed to re-enter atmosphere. And then on the other side, we've got the lunar module, and the lunar module was in two parts. You had this golden lower part that was meant to land on the moon, and then the habitable part, let's say, of the lunar module that was the only one that was lifting off from the moon after the moonwalks, and that was joining back with the common module in order to get the astronauts back on Earth. And if you have a telescope today, and that you look at specific places on the moon, it seems that if your telescope is powerful enough that you can make out the reminder of the lunar modules that have been left over by the various Apollo missions, from Apollo 11 to Apollo 17, with the exception, obviously, of Apollo 13. Anyway, so throughout this presentation, I will refer to the common module and the lunar module. So this is what I'm talking about. Okay, with that with that taken care of, a fascinating thing about the Apollo missions is that although computing was much more primitive than it is today, we are really talking about the infancy of computers and the very first high-scale computing systems in human history. What's fascinating about it is that the way they implemented the IT architecture to support the moon missions was literally an example of edge computing, even before the edge computing itself was invented. It's really fascinating. And the same can be said about IoT, right? I mean, when you think about it, the whole point of the IT infrastructure in a space mission is to monitor the spacecraft, monitor the astronauts. So there are thousands of sensors involved, and you need readings, at a very high sampling rate from all of those sensors to ensure that everything is all right at any time. And so in the case of the moon missions, the common module and the lunar module and the service module are also were equipped with lots of antennas, lots of sensors, and each of them were communicating back to Earth over a 48 kilobits per second connection. So, although it was probably a bit slower, this is roughly comparable to the kind of bandwidth you could get from a phone internet connection back in the days, back in the 90s. So each of the spacecrafts had this connection back to Earth, and the NASA installed a network of 3 distinct antennas, one in California, one in Spain, and one in Australia, in order to be able to follow the spacecrafts at any time. So those 3 antennas, they had UNIVAC mainframes of a specific model, right at the antenna in order to aggregate the data, massage it, and send that back to the mainframe that the various screens in the Houston command and control room were connected to. So that's the photograph on the left. So you see how those consoles look in the day. In fact, they restored some of those command rooms, so you can go now to Houston and visit that and have an idea how it looked. But anyway, all of those screens that you see on the consoles were in fact connected to an IBM mainframe that was able to process about 2 kilobits per second worth of information. Okay, so really the task of the UNIVAC mainframes right by the antennas was to simplify, aggregate the data, and send that back to the mainframe in Houston. And the mainframe in Houston, which wasn't a top-of-the-line model, it was a middle-range model, so not the most powerful that could be available at the time, but was to feed the video feeds on the consoles. And just to give you a vision of how much sensors were involved, I put a little diagram on the right end of the slide, where you see an example of the instrument unit slice in the Saturn V rocket. So there was a whole slice in one of the stages that was dedicated just to sensors and all sorts of electronic equipment. And so just to reinforce the fact that the Apollo missions are a prime example of edge computing, but they are a fairly good example of IoT at work, even before there was an internet or even before IoT was a term. So it's really incredible. I mean, those people were literally pioneer and invented everything from scratch in order to land people on the moon. And this is an incredible achievement. And the one little unknown thing about this is that the whole software team for the Apollo missions was led by a woman, Margaret Hamilton. So go woman in tech, we need more of you. And it's fascinating to see that, a woman, which is little known today, was leading all of those efforts. And the software that they delivered throughout the mission, I mean, it was, there was never a bug that impacted materially the missions during all of the Apollo missions, which is absolutely incredible when you think about it. All right. So before we get to the lessons, I mean, the one thing to know about the Apollo missions is how incredible the Apollo guidance computer was. So you see the computer itself on the background of this slide on the left. So that was a box roughly weighing 70 to 80 pounds, so that would be roughly 50 kilos or something like that, maybe a bit less. And so that's the big golden box, and what you see on the right is the Apollo guidance computer user interface. So there were no bright screens or anything like that. This is literally what the astronauts had to deal with in order to start programs on the computer, check values in real time, check the telemetry, everything. Okay, and so it's called the DSC because essentially you were using this little keypad there, which is astronaut size. Imagine the big gloves that they were wearing. So they were punching codes in order to do things, and really that's all they had. They had plenty of other instruments, okay, but to interface with the computer, this was all they had. And so the way it worked is that you punched the numerical code for a verb, let's say display, okay, and then you punch a numerical code for a noun, let's say current thrust, and then you pushed enter. and this displayed a specific value on the screen. So it was very primitive. But what's fascinating about the Apollo guidance computer is the fact that it was built from the ground up for this mission. And there were a few specific qualities about it that made it incredibly well suited for the task it had. One particular feature it had is that it didn't have lots of memory, about 76 kilobytes worth of memory total, but most of it was ROM. In other words, the programs that the computer was running were straight hard-coded in part of the memory. And so it just had the equivalent of 4 kilobytes of memory to store all of the values for all of the running programs. But the computer was incredible because it was able to run several, it was capable of multitasking. But not only that, if the computer ever rebooted, it was instantly able to restore the state of every of the programs that were running, and to then restart every program in their order of priority. Okay, and that was a critical feature because throughout the missions that we will see, they had to restart that computer multiple times. Okay, but if you restart it and it loses every value, then since the computer is directing the thrusters, is measuring the altitude of the craft, its position in space, and all other life critical features, if you reboot it and you lose everything, then obviously you're not in the right place. You are putting the astronauts at risk. So since everything in a space mission is life critical, the computer was able to restore all of its tasks and reread from memory all of the current values and restart every program exactly where they were, at the precise line of code that they were at the point the computer was previously rebooted. And this was an incredibly useful feature. The other fascinating thing about the Apollo guidance computer is that it was using virtual machines before virtual machines were a thing. So, if you look in depth at the code, it's not VMs really, but the way it was treating every program, every program was executing in a segmented space with its own memory space and that kind of stuff. And all of that was taking turns accessing the hardware. And, it was literally VMs before VMs were a thing, if I simplify a bit. And that was another critical thing about the Apollo guidance computer. So what can we learn today from the design of the Apollo guidance computer in terms of edge computing? Well, the main lesson there is architecture for reliability from the ground up. If you are about to deploy an edge computing solution in an oil and gas refinery, or on a plane, on a warplane that would be deployed alongside other equipment in the sky, or whatever, you need to think about those things straight from the requirements collection phase, okay? And this means you have to use hardware and protocols that assume that the networks will be unreliable and the hardware will be unreliable and all of that, and code accordingly. It's really important. If you don't think you will be able to add reliability down the road after you got your minimal viable product out of the way. That's not how it works. You have to architecture reliability, bake into the design of your solution. Then, second lesson is to be stateless whenever possible. The Apollo guidance computer, yes, it stored values in memory, but the code was stateless, and this meant when the computer rebooted and all of the programs restarted, and there were 5, 6, 7, 10 of those programs running at the same time in a specific order of priority, then obviously the fact that they could be restarted at the very same line that they were at the moment of the restart, and the fact that they could read from this shared memory space the current values for the various variables they had, this meant the code was stateless, and this literally saved the life of astronauts. And this could literally save lives in your case too. Statelessness is really important because it means that your solution is more robust, and at the same time that it can scale more and better. And then finally, virtualize and containerize. And obviously with cloud native and even at the Eclipse Foundation, we have Edge native, you know, containerization, virtualization is a given, but maybe there are scenarios where you have smaller boards, smaller units, and that kind of stuff, and you hesitate maybe about virtualize and containerization, but really those things are lifesavers, literally. And the fact that it was baked in the design of the Apollo guidance computer shows how valuable those things can be, even when the hardware that you have is very low powered. All right, now let's get on specific incidents that happened during Apollo missions, and let's see what we can learn out of them. And we start with Apollo 11 and the famous error 1202. Apollo 11 was the first Apollo mission where we had, you know, people walking in the moon, on the moon. It's 51 years ago at this point, and it's really an incredible achievement when you think about it. But the thing is, what a lot of people don't know is that there were many IT glitches during Apollo 11, and some of them could have led to the abort of the moon landing, or even to life-threatening incidents, or even you know, some of them would have been grave enough to kill the astronauts. So focusing here on error 1202, imagine yourself, you are Neil Armstrong or Buzz Aldrin. You are strapped in the lunar module and you are descending towards the surface of the moon, typing all of the nouns and verbs to execute the specific moon landing programs that the computer has to execute. And then you start receiving error 1202. The problem is you have no idea what this means, okay? The computer was communicating just through those numerical error codes. So some of them were very familiar because, you know, you had many rehearsals of the moon landing, and you experimented with the guidance computer on the ground before the mission. So they trained for months and months and months for that. But error 1202 was a little known code, and it wasn't obvious what it meant. And the people that they were talking to in Houston at the time, imagine you are descending towards the moon and you have to make decisions in a matter of minutes about whether aborting the descent or not. And you have no idea what this code means. And the people they were in touch with in Houston didn't know either, but there was a guy on the team that made up a cheat sheets of all the code, so he could cross-reference the code very quickly. And what error 1202 meant was that the computer was out of memory. Okay, so it was running out of RAM, so it couldn't allocate memory for new variables for the programs that were running. So what was it doing? It was automatically rebooting. And it wasn't a problem to reboot because of the design of the computer. So since the program that was controlling the thrusters for the descent was the most important, then it was restarting first. And after that, the program that was calculating the position of the spacecraft, and et cetera, et cetera, et cetera. And so the engineer on the ground looked at his cheat sheet and said, okay, we are running out of temp space. It's not a problem. You can ignore it. And they ignore it for several minutes. You know, the error popped back again and again and again. They restarted the computer again and again and again. And ultimately, they landed and the mission was successful. This is literally incredible, right? After the fact, they investigated and they figured out that they were receiving this error because, and I'm simplifying here. So if you are already knowledgeable about this, you will find that my explanation is a bit lacking there, but in interest of time, essentially there was a radar that was defective and flooding the computer with way too much data. So the computer was storing those values and at some point was running out of space. But since this was a secondary program that wasn't very high on the priority list, it was okay to restart the computer. And then since it was a very low priority program, all of the life-saving programs for the thrusters and the position were restarting first. And so, you know, they could still continue the descent with minimal disruption. Okay, so what can we learn from this incident? Well, first would be maybe to use something else than just numerical codes in your error messages, right? But this was a basic part of the design of the computer, so they couldn't fix it. But what else can we learn? I think the huge lesson there is to pick the right sampling rate. So don't oversample. I mean, obviously, if you are building a connected car or a solution for a connected locomotive or a warplane or whatever, obviously you need, real-time data, maybe 1,000 times a second, and it's fine. But if you are building a solution for a smart building and you want to measure temperature and humidity in all the rooms, maybe you don't need those values 1,000 times a second. Maybe every 10 seconds is fine, right? And that's really important. Then when you receive data, maybe you don't need to process all of it right away or even to process all of it. So just process what you actually need and don't assume, oh, I have plenty of headroom on this CPU, it's no big deal. Even if I don't need the data, I will process it right away. No, you don't know when the load will be more important and that you will receive more data. So design for efficiency is really important. And then the third lesson is that sensors can go haywire, and you have to design around that. The problems with the Boeing 737 MAX is a good example of that. They had only a single sensor to calculate the angle of attack of the plane, and this led to 2 catastrophes where hundreds of people died. So if they had redundant sensors, this wouldn't have solved the problems in the software of the plane itself, but at least, the whole system would have been more robust, and probably the tragedies would have been averted. So design around the fact that you process just the data you need and assume that your hardware will go bad, and then you will have a much more robust edge computing solution. Now let's talk about Apollo 13 and its famous air filters. So Apollo 13, I'm sorry if you didn't see the movie. So spoiler alert, they were en route for the moon. There was a big incident and they had to literally improvise on the spot for 2 and 3 days in order to get the astronauts back to Earth alive. Okay, and they were successful. So sorry if I'm spoiling the ending there. But what's fascinating about Apollo 13 is the sequence of events that led to the incident, and then how they were able to do many, many things in order to save the lives of the 3 people on board. So what you see on the background of the slide is a photograph of the common module where it exploded. And that was the incident that happened that threatened the life of the astronauts. So what happened is essentially, as they were building the service module here on the ground, they dropped just by a few centimeters one of the tanks that was to contain the fuel and oxygen on the ground. And those tanks, they were equipped to be able to eat their contents, because obviously space is very cold, very close to absolute zero. So you need to eat the oxygen and the nitrogen and the fuel that are in those tanks in order for them to stay liquid and be able to burn it. Okay. So from time to time, the astronauts had to start heaters on those tanks to keep the contents in the correct state. And the problem is that when they dropped the tank on the ground, one of the cables inside was damaged, which means at some point during the flight, when they started the heater, there were sparks that were emitted from that damaged cable, and that literally started a fire and then provoked an explosion in one of the tanks. So obviously that was a very dangerous situation, and it was especially dangerous since it was the service module that was damaged. So that's literally their base of operations. The common module itself is just a capsule. It doesn't contain the fuel, it doesn't contain the oxygen that the astronauts need. And then they had the lunar module that was intact, but the lunar module is not meant for atmosphere reentry. And obviously it was out of question to try to land on the moon. But they had to devise a situation where essentially they would try to save as much resources as possible from the service module, and in order to be able to return to Earth, because they were en route to the moon, so they had to uh, circumnavigate the moon and to get back to Earth on their current trajectory, and after that re-enter atmosphere in just the command module. But in order to do that, they needed to use the lunar module as a kind of lifeboat, and so use the oxygen and fuel in the lunar module as they were spending 2 or 3 days in space before being able to get back on the ground. And well, the lunar module wasn't built for that at all. And one of the problem there was with the lunar module is that there weren't enough air filters in it to be able to serve a crew of 3 for 2 or 3 days. Okay, it wasn't designed for that. They had just enough air filters to do their little moonwalk and get back, and after that the common module was supposed to take care of stuff. The problem being is that the shape of the air filters in the command module was different from what they had in the lunar module, and we see that on the next slide. So you see this square lunar command module filter that somehow they had to devise a solution in order to use on the round openings that they had in the lunar module. And what they did is that they had to devise on the ground very quickly in Houston a solution to make those square module literally fit the round opening somehow. So they put a team of engineers in a room with just the objects that the astronauts had access to and told them, you need to find a way to fit the air filters from the command module in the lunar module. Do it. You have 3 hours to devise a solution. And in the end, as you can see on the photograph, they devised something which is incredible. But I mean, there's a lesson there. Obviously, if they had used a standard size and a standard shape for the air filters, they could have reused straight away the filters from one spacecraft to the other, right? So the lesson there for edge computing is standardization pays. Stick to open and vendor neutral platforms. That's really important. Kubernetes belongs not to Google, but to the CNCF, right? And that's a great thing because it means there's a neutral third party ensuring there's a level playing field, okay? And the second lesson there is a bit less obvious, but the best platforms are hardware aware in the sense that when the software is aware of the capabilities of the hardware, then obviously it can do more in a more efficient way. So in this case, the software in the lunar module and in the common module wasn't aware of at all of whatever problems were happening in the various spacecrafts. And the software for the both spacecrafts, it was designed to operate independently, but they never thought about, let's say, oh, let's recirculate air in the joint spacecraft in this and that fashion in order to save our lives, okay? Which could have been an alternative to work with the air filters there. So if the software had been hardware aware that, hey, we are not running in command module mode only, but rather in command module plus lunar module mode, then maybe they could have more easily shared the resources between the two spacecrafts and then essentially save the lives of the astronauts easier. So there's a big edge computing lesson there, and certainly run away from solutions that are proprietary. If you want to do edge computing right, you have to do it the open source way. And not only the open source way, because not open source is the same, but use open source that is stewarded by vendor neutral operations like, well, the Eclipse Foundation or the CNCF or the Linux Foundation, and then you will be in a much better place. All right, which brings me to the Edge Native Working Group at the Eclipse Foundation. So essentially, all of those lessons that I covered today and many more, we try to apply them to edge computing in the Edge Native Working Group at Eclipse. And essentially, this is a gathering of organizations that is code first, because yes, we have blueprints, we care about architectures, but essentially we started from working code, production quality, commercial grade code that you can use today. We have two distinct platforms, and I will tell a bit about that on the next slide. But essentially, we started from the code first, and then learned the lessons from that. We care about streamlining mass deployments for Edge, because this is when you try things at scale, it is then that you see the issues and that you have to solve it in the most efficient ways. And our goal is to promote the use of what we call Edge native DevOps, or Edge Ops. And these are the current members for the working group, always looking for more. So if you are interested in join our members in there, it's the door is always open. And what I would highlight is that it's only IT companies there. It's not only IT companies there, but we have players, industrial players like Bosch and Siemens, that are looking at the tech and trying to see how they can leverage that in the industry and even deliver new products, innovative platforms in the market using our technology. The two projects that we have are Eclipse IO Fog and Eclipse Fog OS, and both represent a distinct take on edge computing. IO Fog is centralized container orchestration. So there's a central controller in there, and it cares mostly about containers for the time being. And Fog OS is a completely decentralized edge platform that can rely on containers, that can rely on virtual machines or straight binaries, and defines a unified compute fabric. And both can integrate with Kubernetes in different ways. So if you care about Kubernetes and want to really scale down at the edge, then both Eclipse IO Fog and Eclipse Fog OS, it's written Fog 05, but it pronounced Fog OS. So both platforms can be used right away. And when you look at the wider Edge ecosystem, you see there are many, many projects. But when you look at what we have at Eclipse, not just IO Fog and Fog OS, but all of the other development frameworks that we've got, all of the other projects we have in the IoT space, like Hono, which is a message routing platform, or Scopper from Red Hat. That's not an Eclipse project, but we work very closely with them. Anyway, when you look at everything that we cover in the edge to cloud continuum and on the development to operations continuum, you will see that we have unparalleled coverage there. Anyway, if you want to learn more about Eclipse Edge Native, please visit our website, follow us on Twitter, and obviously you can follow me on Twitter as well. I'm a Blueberry Coder, so please feel free to reach out there, or on LinkedIn, or whatever. You will find me online one way or another. So thank you so much for listening today.